So maybe before I start, let me just, because I know I'm going to forget at the end, okay, 100% likelihood, okay, 1 minus epsilon likelihood. So I think we should just take a moment to thank Florent and Lenka, since this is technically the last lecture, for setting this up. Maybe just give them a brief round of applause. Yeah, so I mean, I think for many people here, this is like one of the best events on theory of deep learning that's been put together, especially because of the pandemic and things had to be online for a while. So it's much appreciated, I'm sure. That's everybody's sentiments. Okay, okay, returning to the lecture. So in the morning, I told you about how to compute statistics for random networks at finite width. And somehow the upside of all that is we could do it for any nonlinearity, any number of inputs. I didn't really explain how to do corrections to dynamics, although in principle the techniques are similar. They're just more complicated. So if you want to see the end of the proof, which I kind of got through, like, let's say 2/3 of in the last lecture, come tell me, and I will do it for you offline. But I think the feedback I got from people is like time for new ideas. Okay, so I'm going to tell you about how specifically to think about random value networks. Okay, you can't do other nonlinearities that I know of this way. But unlike the other case of a general nonlinearity, here there will be exact random matrix models. There will be combinatorics. We'll get all kinds of things which for me are really exciting. Okay, and you'll tell me if they're exciting for you as well. Okay, so here's my setup. Let's just recall the notation. So my setup was like this, right? These were the pre-activations in layer L+1, neuron I, input X alpha. And I had a bias. And then I also had some weights. Okay, we all have biases and weights. I'm not special in this case. J sigma of Z L J alpha. All right, very nice. So what I'm going to do in this lecture, like I said, is I'm going to specialize to the case of ReLU. So this lecture. So I'm going to say sigma of t is t times the indicator function that t is positive. That's just my notation for the ReLU. I'm going to, for the most part, just because it's slightly easier on the notation, remove the biases. So B, L, I are going to be identically 0. And then for the distribution of the weights, okay, if you care about such things, I'm not only going to do Gaussian, I can do any distribution you want in the same way. So why not do it? So for the weights, I'm going to write WLIJ is the square root of 2 over NL minus 1. So I'm going to do things in the NTK parameterization times what I'll call W hat Lij. Okay, and these W hats, maybe I'll write it here, W hat Lij, are drawn IID from a measure mu. So this is just a probability measure on R, and I want it to have two properties, okay, which I'll put in a slightly different color because I can. So I want this measure to be symmetric around 0. Okay, just like a uniform distribution with mean 0 or Gaussian or something like that. And so therefore it has mean 0 as a result, and I want the variance to be 1. Okay, those are my two conditions on mu. So if this is a standard Gaussian, then we're back in the usual kind of setting. Okay, my goal for this lecture is to describe a different set of techniques for understanding random ReLU networks than we had for general networks. So let me state it here. Goal. So describe formalism that gives basically all the answers you might want. Answers, okay, how to spell it like that. For sigma equals ReLU, okay, at a single input. So this technique has some downsides. So I'm going to call my input X alpha. Just a reminder, it's an Rn0, okay, and I'll take it to be non-zero. Okay, so this technique is special. It can only tell you everything, at least in the way that I'll present it, about a random ReLU network evaluated at a single input. But on the other hand, I'll be able to see the full L over N dependence and everything. So let me try to state a result and draw my picture that I like. Okay, so here's the theorem that I will prove a little part of. Okay, it goes like this. So let's set xi kind of like before, except this time I'll have a 5 for reasons that, are a little hard to explain, except that 5 is 3 divided by a half minus 1. Okay, that wasn't very helpful, but nonetheless, so that's my xi. So here's what you get for these random ReLU networks. Let me state 3 kinds of results, and you'll see L over N appearing. And let me simultaneously, I suppose, draw the picture. Okay, so reminder, I like to draw L on the x-axis. N is my layer width. So here, N sub L is the width of the Lth layer. And I remind you, just like last time, all these NLs are proportional to a large constant N. Okay, so up here, where xi equals 0, this is the NTK regime in the way I'm scaling things. Xi equals infinity over here, and this is the kind of like untrainable regime. And the picture I had before is that to interpolate between these two regimes to understand what happens, it's productive not to think of L and N separately, but rather to think of their ratio. And somehow along this curve, that's how we think about deviations from the NTK regime in a way that knows about the role of depth. Okay, so let me make this more precise now. So one object that you might want to consider is sometimes called the input-output Jacobian. Okay, so what do? I fix my favorite component of the network input, let's say the pth component of x alpha, and I take the derivative of my favorite component of the network output, let's say q alpha. Okay, and I square this thing. Okay, it's just what's the partial derivative of the network output at this input in this particular direction. And what I'm going to show, okay, I'll show part of this today, is that I'm not going to compute moments. Well, you don't have to just compute moments, but you can get the whole distribution of this thing, even for non-Gaussian weights and everything. And just like before, when we did the Gaussian weights calculation, this will look like exponential with mean minus xi over 2, variance xi over 2 in the Gaussian. Okay, so if you want, this is saying that if L over N is not too close to 0, you have very large gradients in your network. Your network looks very, very spiky at initialization. And like I was saying last time, this is meant to be a remnant of the fact that as you go in this direction, as you increase xi, you get more unstable. Okay, so that's one very particular sense. So another point, okay, we've talked a semi-infinite amount about the NTK. Some people love it, some people hate it, but okay, we all have to deal with it. Right, so if you wanted to ask, what's the fluctuations of the NTK? So you can take the NTK, you can evaluate it at my fixed input x alpha on the diagonal, and you can ask at initialization, how fluctuating is it, right? Part of the NTK result is that if you fix the depth of your network and you go out to infinity in the width, the NTK converges to its mean. The fluctuations go to 0. Okay, and actually what you get is that this is exponential in xi minus 1. Okay, I'm dropping a bunch of constants. That's what that twiddle means. Okay, so indeed, if you fix the depth and the width goes to infinity, xi goes to 0, and you get that the variance is 0. But actually, really, if xi is like even 0.1, this is really a not totally negligible number. Okay, you get non-trivial fluctuations in the NTK. And this is just kind of the start of a very long story, which I'll make epsilon dynamical. So, yeah.
Can you just repeat what's the y with respect to?
Yeah. Initialization.
Okay.
So you fix an input, you randomly initialize. This is my distribution on the weights. And I ask, how much does my NTK fluctuate? I know that up here, the NTK converges to its mean, so its fluctuations go to 0, but not over here. That's what I'm saying. Okay, very good. So the other thing you might ask is, suppose you take a batch of size 1, and you ask, how much does the NTK change after one step of gradient descent? That's still a calculation about init. Okay, and you can extend this if you work really hard to do a dynamical thing throughout a trajectory. But OK, I don't know how to do it directly for ReLU networks. I have to use the techniques of the previous lecture. And what you find is that this is xi times exp of xi. That's how it scales. So again, if xi goes to 0, The change from one step of gradient descent in the NTK goes to 0, as it should. That's what we know. But if xi is positive, actually this thing starts to grow exponentially in xi. It's kind of very, very sensitive to this kind of parameter. And this tells you that L over n, in this sense, controls the deviation from the NTK regime, at least after one step of gradient descent. Okay, so some features will be learned, but I don't know which ones, okay, at least at this level of discussion. Okay, so I'm really mainly going to focus on A, and if I have time, I'm going to try to show you how to compute not the variance, but the mean of the NTK. But all these calculations will be exact at finite width, finite depth, everything. I'm not going to have to take asymptotics in them, or at least not really. So you'll see how that works. But let me just pause and ask if there are questions about the setup.
Yeah, so just if you can say again, that example means a step of gradient descent, seeing example x alpha over.
Yeah, exactly. So you know, I have this unfortunate constraint. Okay, I would love to remove it, and I don't know how to very systematically, that I can only say things at a single input. So the best thing I know how to say is I look at the on-diagonal element of the NTK, and I ask how much does it change if I use a batch, you know, consisting only of x alpha comma its label. So I can do that calculation. Of course, in reality, you don't use batch size 1, okay, and so on and so forth. But at least I can do an exact calculation in this.
Are you implying like a fine step size or some gradient floating? Or
Yeah, so I'm,
variation, or is it,
right, so I'm suppressing some constants, you know, so of course there's going to be a step size, that everything's linear here in step size.
It's, we're not talking derivatives, we're talking variations.
Yeah, that's right. You can do it at finite but small step size. I mean, from that point of view, like, you know, I don't know the difference between an extremely small step size and doing finite time, and doing like continuous time.
Yeah, sure.
So-
But is there any training? Sorry, step size of what?
So this is, you take the NTK at initialization, and you take one step of gradient descent on mean squared error, where the batch that you use has size 1. It just uses your particular x. And I want to ask, like, how much does the NTK change? Right? Like, somehow at infinite width, you know it doesn't change at all. That's somehow the point of the scaling in this regime. But I'm saying that actually, if you back off the infinite width limit, and you think of depth over width really as the controlling parameter, it actually kind of changes exponentially. So it's very sensitive to this thing, and you can't see this in the kind of the strict infinite width limit. Okay, so let me just say, like, ... Basically, I think of this as a kind of inverse temperature for a random ReLU network, and everything is kind of exponential in this inverse temperature. It's one way you could try to say it. Okay? Not that I exactly know how physicists think about inverse temperature. I just know it appears in the exponent, you know, kind of linearly. Okay. All right. So here's my plan. I told you a little bit the setup for what I want, and I told you the kind of theorem I'd like to prove. And what I now have to do is I have to deliver for you. I have to, you know, make precise this idea that I'm going to describe some formalism that allows me to compute all these things exactly at finite width, finite depth, everything. I get some kind of formulas. And so I have to tell you what kind of thing that's going to be. And I can do that if I find an eraser. All right. Very nice. All right. So the way I'm going to do this is I'm going to say random ReLU networks, at least evaluated as single input, are surprisingly simple objects. So that's going to be the first thing I'm going to tell you about. And then given how simple they are, I'm going to introduce a kind of classical formalism from random matrix theory called path counting for understanding them. Okay, so here's the key technical result. Key technical result. Okay, this is something I first observed a long time ago in some papers, but okay, I've used it a bunch, and I think it's pretty cool. So here's the result. If you look at the output of your random ReLU network at a single input, that's the kind of thing I'm telling you about, then this has exactly the same distribution as a deep linear network, deep linear net, with depth L, just the same, and dropout parameter p equals a half. So I'll explain exactly what that means, but maybe you already know. Okay, put another way, it's the same as taking your weight matrices, WL, and interspersing them with these diagonal masking matrices, or gating terms. Sorry, maybe I should call this DL, down to D1, W1. Okay, so the W's are just the weight matrices. They're exactly what you think they are, but the D's are the following. So DL is just a diagonal matrix, and on the diagonal you get 0 or 1 IID. Okay, so what I'm saying is, to process an input, what you can do is you apply your first weight matrix, and then with probability 1/2, you drop every neuron. You just zero it out. That's what I mean by dropout. Then you apply your second weight matrix, and then independently with probability 1/2, you drop everything out. Okay, so the key is that these D's are independent of one another, and they're independent of the W's. So when people talk about gated ReLU networks, this is the kind of thing they do. And I'm telling you that in distribution at init, you can exactly decouple the gating at each ReLU neuron from the weights of the network itself. It's not completely obvious, but it is true. Okay, so let me pause and ask if it's clear what I'm saying first. No, not yet? Okay. So I think the best way I know how to clarify this is let me write a sketch of a proof. Okay, and I think you secretly already know this, it's just bizarre notation. Okay, so here's a proof sketch. Okay, so what do we know? Well, look, I already turned my biases off, and every time I apply a ReLU neuron, it's just the identity times a mask about whether or not the neuron is on or off, right? So we always have, so in every ReLU network, random or not, it doesn't matter what, that you can write the output, ZL plus 1 alpha, as a product that looks very similar, WL plus 1, I'll call it D hat L, WL dot dot dot, D hat 1 W1, X alpha. Oops, I should put an X alpha here, of course, excuse me. Okay, where my D hat L's are just a diagonal matrix that tell me whether or not my neurons are on or off. So this is just the indicator function that ZLI alpha is positive, and this is I goes from 1 up to NL. I can always write it this way, right? Like I apply my linear transformation, and then if my neuron is on, I keep it. If it's not, I zero it out. So I can write this as a composition of W and a diagonal matrix, which tells me which neurons are off. So this is always true. And the issue, of course, is that when you look at it, whether or not a neuron is on or off typically depends on the weights leading up to it. But the point is that actually it doesn't. So at least at initialization. However, if we are given the, let's say, layer ZL, we're given the vector of activations. So since I wrote L, let me write L minus 1 here. So if we're given the previous layer of activations, what do we know? We know that ZLI alpha are IID, and they're symmetric around 0. Right? If I just give you these ZL alphas, because the B's and W's are independent and symmetric around 0, the whole distribution is independent over I, and they're all symmetric around 0. Okay, so just by symmetry, the probability that the neuron is off is 1/2. And so what you find is that this collection of random variables, ZLI alpha being positive, okay, so what do you know? Well, they're independent of each other, and each takes 1 or 0 with probability 1/2. But in fact, the distribution you get was independent of what you conditioned on. So you find that this whole thing, I goes from 1 up to ND, are all independent. Okay, they're independent for all I. And in particular, you find that they don't actually depend on the values of the weights that you got because you symmetrized on the weights. Okay, so this is my very sketchy proof. Let me not go too much further into it, but trust me that this is true, and that's the basic intuition. If you tell me what happens at layer L, all the neurons in layer L plus 1 are just on or off with probability 1/2, and everything's completely uniform. Okay, so from my point of view, if you just buy this reduction, it's like kind of an amazing fact. Okay, I was shocked for at least a day or two after I realized that I thought this was true. Like, ReLU networks are supposed to be complicated nonlinear things, and this is a product of independent matrices. Like when I was brought up, mathematically speaking, whenever something was a bunch of independent random matrices, like you were very happy. You could calculate if you wanted to. Okay, so let me just pause. I'm not so worried about the proof, but I want to make sure that the statement of this result is clear what I'm saying.
Do you have a reference for where this result is with the full detail?
Yeah. So I have a paper with Mihai and CMP 2020, I think, and this is proposition 2. Well, you know, you want it. I'll send it to you if you want, but I promise it's right there. Okay, so it's amazing. I'm saying every neuron is on independent of every other neuron with probability of half and independent of the weights. That's the beauty of this random ReLU network world.
Sorry, but why is it not contradicting anything we know about expressivity of linear networks and training?
Yeah, so this.
Not training yet, I know, but let's assume we make it very wide, so the training isn't very noticeable. Why are you not contradicting everything we know?
First of all, in these ReLU networks, like if you look at the original NTK type proofs, what they actually show is that most of the neurons never change whether they're on or off. But that's okay because you still have this final layer. You know, it's just like a random feature extractor if you want. It's like a random linear high dimensional embedding, and then you learn some kind of linear combination to match your targets. So it doesn't contradict the fact that we can fit data. And if you're not in the NTK regime, then this is true only at init, and then things start changing, but the changes are correlated. So it's a slightly delicate thing, but it really makes a lot of calculations possible that you can't do in general. Yeah.
It boils down to the fact that the W's are still random, right?
Yeah, precisely.
Whereas the approximatability is needs some deterministic values of W to represent the function.
Yeah.
That's not very important.
No, indeed, I totally agree. As soon as you start setting even the last layer W's in principle, you change everything. Yeah. But okay, you know, in the language of Julia, if I may be so bold, it's a cute observation. Okay, I don't know. Right. Okay. All right. So let me tell you about now how to use this result. So I'm going to write a corollary for this, and to write the corollary, I'm going to make a picture. So let's consider a ReLU network, one that I can actually draw. Okay, so this is like, I read it from left to right, so this is input dimension 2. My first hidden layer width has size 3, then size 2, and then size 1. Right, okay, so here goes my definition. So I'm going to make a definition of what a path is in this network. You probably already basically know. And then I'll tell you how to use this result to write everything you wanted in life in terms of paths. Okay, maybe not in life, that's a little bold, but nonetheless. Okay, so a path through the network, through my network, is, okay, so I'm going to call paths gamma. So gamma, it's just a choice of neuron in every layer. So let me do the picture first, and then I'll do the definition. So the path says I start here, then I go here, then I go here, then I go here. And as you can imagine, once you have a choice of neurons, you can connect them to get a path from the input to the output. So what does this mean? It's a choice of neuron in the first layer, and then finally a choice of neuron in the last layer. Okay, I'm going to call the space of all paths sometimes capital gamma, because I'm a little lazy. Right? And the point is that gamma of L is just one of the neuron indices, 1 to NL. Okay, that's the space of all paths through the network. Okay, so given such a path, so here's gamma of 0. In this case, it's 2. Oops, this is gamma of 1. It's 2. Oh my God. Gamma of 2 is also 2. Okay, gamma of 3 is 1. So that just tells me which neuron I pick. Right, and given a path, you can't help but connect it up like this, and you can't help but say, right, in layer L, the path gamma gives me some particular weight, WL, gamma of L minus 1. Right, so for instance, this is W1 gamma. It's that particular weight that decorates this edge. This is W2 gamma, okay, and so on. Okay, and similarly, you get ZL gamma is just by definition, you know, the pre-activation in layer L of the neuron that this goes through evaluated at my input. I suppress the input. Okay, so that's just my notation. Okay, so that's what I mean by a path through the network, and that's what people typically mean by paths. So if you hear about things like path norm, it's all about this. All right, very good. So now let me write a corollary of this result, which is thankfully still up, which is just a thing you've probably already seen. Whenever you have a product of matrices, you can think of the output as a certain sum over paths times the input. Okay, so if you haven't seen it, here it is. And then I'll stop, and I promise, and I'll ask for questions. So here's a corollary. Okay, so if you wanted to know what, let's say, the qth neuron does in the output, you can write it like this. Okay, so get rid of this. So it's the sum on p goes from 1 up to n0. So I look at all the possible neurons in my input, and those are decorated by the inputs x alpha. Okay, so this is the pth component of x alpha. Then I take all the paths gamma, which I'll heuristically write as going from p to q. P to q just means the first neuron is neuron p, the last neuron is neuron q. Okay, and then you take the product of the weights along the path. Careful to remember that in the last layer you don't have a sigma. So the product on L goes from 1 up to L, WL gamma, times something I'll call psi L gamma. Okay, because I'll need to write it a bunch of times, where psi L gamma is just the indicator function that C L gamma is positive. It's just the indicator function that this path is on. Okay, so this is just saying that to compute the output, what you do is you sum up over all the paths from the input to the output that are open. In other words, that only go through neurons where the ReLU is on. And for each such path, you take a product of the weights along the path. That's the kind of thing you get. Okay, so this is a nice corollary, and the point is, okay, and the WC, these like indicators that things are on, and the WL gammas are all independent. That's the point of having all your masking matrices be independent of the weights. Okay, so I want to just pause for a second and first of all ask if the formula makes sense. But second of all, point out that, you see, I haven't taken any expectations or moments or anything like that. This is just an exact formula for the output given the input. And if you like combinatorics of these paths, and I hope at least for this lecture you will, you can write down any moments, any expectations, anything you want just in terms of these paths. And I'll show you the yoga that one needs to get that to work out. Okay, so are there questions about this or comments about the setup? I want to make sure that this is clear because I want to work with these paths, but I don't want to speed through it.
By only left, of course, you mean that, I mean, zeta L gamma depends on all the weights that I'm saying. So
no, so that's what I'm saying. Because of this, it's independent. So you know, like normally, if you didn't have a random ReLU network, then of course whether or not a neuron is on depends on the weights. But because I told you that in distribution it's the same thing as just taking the neurons to be on or off independent of the weights, these psi's are independent of the W's. That's the reason you can use this. Otherwise the dependent structure is going to be too painful. Yeah. No questions? Okay, attack. Time to attack. All right. Oh my God, that's really bad. Yeah. All right. Much better. Okay, so I want to show you now how to use this to actually calculate something. I promised you some exact calculations, and so far I've just been talking, although maybe that's all I ever do. Nonetheless, so some examples of things that I want to calculate, and maybe you want to calculate as well. Right, so let's suppose I wanted to calculate this thing I was telling you about in the theorem. I have some neuron in the output, and I want to take its derivative with respect to some neuron in the input. Well, what do you see? Oh, it's not too bad. Everything is just linear in the x's. After all, your ReLU network is piecewise linear, and we're just evaluating at a given x. So what do you get? You simply get that this is the sum over all the paths from p to q. Right, so again, p is which neuron here I'm differentiating with respect to. Q is which neuron in the output I'm taking the derivative of. And then I just copy the rest. Okay, get the product. Maybe I'll be careful. WL gamma, product on L goes from 1 up to L. WL gamma psi L gamma. Okay, so that's not too bad. It's not too bad, not too bad. Okay, suppose we want to do something slightly more interesting, like people are interested in the NTK or in general actually training some weights. So as you know, one of the things you have to calculate is the distribution of the derivative of the output, let's say of some neuron, with respect to a weight, WLIJ. Right, so I have some particular weight. Okay, I'm going to use a color people didn't like as much, but life is tough. Okay, here's WLIJ. And now I'd like to calculate the derivative of this thing with respect to this WLIJ. Okay, so just to make sure I'm not talking only to myself, which, you know, is the usual default state, right? What am I supposed to do to this formula?
Just take the paths that go through this edge.
Yeah, exactly. Very good. So now he's saying, look, these indicators are either 0 or 1. Their derivative is 0. So all you have to do is make sure you have a W in this path. And if you have it, it just cancels out. And all the other paths go away. So indeed, you just get the sum on P goes from 1 up to N0 of X P alpha. And then you get the sum over the paths from P to Q. Okay, and then I'll be very careful. So gamma of L minus 1 is equal to J. Gamma of L is equal to I. That's just my way of encoding that my path has to go through this neuron at layer L minus 1 and through this neuron at layer L. And then I take the same thing. Right? I take WL plus 1 gamma. I take this product. Okay, it looks horrible. If you think it looks horrible now, just wait till later. But nonetheless, WLIJ. Okay, you just get rid of it. You just differentiate with respect to it. That's how I'm going to write. Okay, so my point is that the first step of all the proofs that I'm going to try to explain to you and all the things that I won't prove for you is just to realize that anything you want to compute can be written as some sum over paths with some restrictions potentially on the paths that you get. All right, very nice. So what I want to do is I want you to come away from this with actually knowing some kind of technique, and I can't show you the technique without doing a calculation. So I have in mind, okay, when did I start? Oh my good. Okay, I had in mind 3 calculations, and we'll probably do 1.5 calculations. Okay, but I'm going to show you the yoga of the paths. It's not so bad once you know the way. Okay, so here's my plan. I want to prove the following theorem. So I'll actually do these calculations. And these calculations, I think, are really cool. Okay, so at any finite width, finite depth, anything you want, the following is an exact formula. If you take the expectation of the derivative of the output of your network, take some neuron with respect to some neuron of the input, squared. Okay, you just want to know what's the typical squared size of my gradients. I claim that this is exactly equal to 2 over N0. That's a nice thing. There's no asymptotics, nothing there. One of the yogas of the paths. Okay, so you might say, oh, well, this looks really good, right? On average, my gradients, at least in this sense, are not too wild. And so maybe my ReLU networks are always trainable. Okay, and that's false, because the mean of a random variable doesn't tell you about its fluctuations, after all. So, okay, then you have to develop the yoga slightly further, and you can try to compute the 4th moment, xp alpha to the 4th. And what we find is like this. So if I have time, I'll show you all of this, but let me get the result exactly right. What do I get? Sorry, where is it? Oh yeah, here it is. So I believe that I get 6 over N0 squared times the exponential of 5 times the sum on L goes from 1 up to L of 1 over NL. Okay, plus corrections that go to 0 like L over quantity N squared. So unlike before, okay, where I was only able to extract leading order in L over N, I get the full dependence in L over N, okay, plus corrections that go to 0 if L over N is bounded. Okay, so you get much more from this path formalism. Okay, you can compute all the moments. Okay, at some point I computed all the moments in a paper, and it was both fun and painful, and recommended and not, and all the things. Okay, it just depends on how you're feeling that day. Okay, so let me just pause for 1 second and say, you might say, okay, again, who cares about any of this, which is like a fair point, right? But one thing you learn from these 2 statements is that and this gets back to a question that was asked before. I don't remember who asked this. So you might ask, well, when are networks numerically stable enough to start training? When are the fluctuations not too big? Okay, here I'm doing input-output Jacobian. You can do the derivative with respect to the weights as well. And you see that the mean is always reasonable, but the fluctuations are exponentially large in L over N. And so you're going to have exploding and vanishing gradients if and only if L over N is large. That's like kind of one simple and practical conclusion. Okay, so I don't have this picture anymore with the semicircular arc. But as L over N gets bigger, things become less trainable. What can I tell you? Okay, and this is true. Of course, if you add batch norm and res and this and that, things become more trainable at large depth. But like people to this day have to deal with exploding and vanishing gradients, and like at least in this simple case, you can really get your hands on it. Okay, very good. So are there questions or comments about the thing? So I want to actually now do these calculations. That's my goal. I'm certainly going to do this one, and then depending on how much time we have, I might do this one, or I might compute the mean of the NTK. You can do that one very easily too. Depends what people are excited about. Okay, questions? I'm going to erase. Okay, I can erase all of this. I do believe. All right.
Boris,
Yeah.
is it already apparent why it may be difficult to use different inputs like x of x beta?
Yeah, okay, good point. I should have said something about that, and obviously I forgot. So here's the problem. The problem is that this is true marginally for each alpha, but whether or not a neuron is on or off depends very much. They're correlated across inputs. Right? If I take two nearby inputs and I tell you a neuron is on for one of them, surely that tells you a lot about whether it's on for the other one. And now all of a sudden you have a complicated correlation structure. And okay, it seems complicated to me. Maybe somebody in this crowd will figure out how to make it simple. You know, I just don't know how to deal with it. Yeah.
Maybe one way would be to look at random gated networks where the gating neurons are independent from the value neuron, from the linear neurons.
Yeah, so if you did that, then everything I do will literally transfer over to multiple inputs, just because you're by hand enforcing this thing, certainly. And then the question would be like, how bad of an assumption is that? And then you could try to answer that empirically, and presumably in some regimes it's not so bad.
You will have used one of the lectures. Who talked about those? Hanin, yes.
Right. I mean, so people do use it, for sure. So you can apply all of this to gated ReLU networks. You're totally right. I don't know how in general to prove a theorem to say the two are close if you wanted to talk about honest ReLU networks. Okay, or somewhat honest ReLU networks. I use mean squared error, no batch norm, you know. My level of honesty is bounded. Okay. Very good. Other questions or comments? Yeah.
A very annoying statistical physics question. Is there a setting in which this is not a crossover but a phase transition? Where you go with a specific L over N?
I don't know. I don't see any phase transition here. Everything is kind of smooth in L over N as far as I know. But what do I know? Okay, I know a little bit, but not that much. so maybe, I'm not sure. Yeah.
They just have like about the setting, because
Yeah.
there's another problem that kind of reminds me of this setting with random weights and just one sample. But then the problem is the following, whether actually from observing the output of the network, one can actually infer the input. So is that, but that's maybe.
So one thing to say is you could try to, the best you could hope to do, I think, in this setting is infer the norm of the input, just given that everything's rotationally invariant, you know. Like if your weights are Gaussian, for example, you can't hope to.
They're fixed, right? Once you fix them and you know them, then.
I mean, so I think you're asking something about injectivity, you know, right? Yeah, so certainly people study that, and I think you can use these techniques to try to understand when ReLU networks are injective, but you're going to have to study more than one input. You know, it's not much fun to study the injectivity at a single input. And so it's going to, so I don't know the exact relationship between those two, but that's quite an important question, like for doing compressed sensing or for whatever else. You'd like to have an injective. Yeah, definitely. I think that's really interesting, and I'm not sure how to do it. Okay, so let me try to compute the mean. I promise it's not so bad. So here's the proof. Okay, we can do it. Okay, so here's step one. Okay, step one is to introduce the paths. So let me draw a picture and write the formula. So okay, unfortunately I erased my network from before, but it's okay. It wasn't very big. There it is. Okay, so I fix, in this case, I just have one output neuron that I could possibly fix, and I fix some input neuron, right? And I want to compute the expectation of the derivative of my favorite output neuron with respect to my favorite input neuron, oops, P alpha. And what we already decided is we have a formula for the thing inside the square using paths, right? This is the sum over paths gamma from P to Q. And then we take the last layer weight, and then we take this funny product of things about the weights times the indicator functions that the neurons are open. Oops, just like this, and that's like that. Okay, so not too bad. So now you see what's going to happen. I'm going to square this, and I'm going to have two paths. Right, so I'm going to have maybe path gamma 1. Maybe that's gamma 1. And then I might have path gamma 2, so I should probably use a different color. I don't know if people can see these colors, but okay, hopefully. So maybe they're together at first, then they decide to break up, and then like all good movies, they come back together. Right, so maybe those are my two paths. So I'm going to get this kind of double sum on gamma 1, gamma 2 from P to Q. Okay, and then I'm going to have the expectation, and I'm going to have this big product, right? I'm going to have the product on K goes from 1 up to 2 of a bunch of stuff. I have the weights of path gamma K, and then I have all the other weights, WL gamma K, psi L gamma K. Okay, so whatever it is, it's going to be something about the combinatorics of these paths. And in this case, it's going to be very simple, as the answer suggests. So what's the point, right? The whole point that I was telling you is that all the W's and all the Xi's are independent. Okay, and like you just have to use that. So let's use it. Okay, so I'll say step 2. Step 2, use independence. Right, so before this, I didn't use anything about being random. This was just a formula. Okay, I'm going to erase this. All right, very strong. So what do I get? I get this is equal to the sum over two paths, gamma 1, gamma 2, that go from P to Q. I hope I wrote P to Q. I did. Right, and I get the expectation of the product of the weights in the last layer, WL gamma K, oops, L plus 1, excuse me. And then I get the product over all the other things. So I get the expectation of the product of the weights in layer L. Okay, I apologize for writing things in such brutal detail, but I don't know how else to see it. And then you get these indicator functions. Okay, so let's play my favorite game, which is put the audience on the spot. Okay, it's actually not my favorite game, but it's up there. So, okay, what's going to happen?
You will get contributions only where the paths are low and close.
Aha. Exactly, right. So it means you remember the statement of the problem. Right? The point is all these weights are independent and mean 0. And so note, right, that the expectation of this product on K goes from 1 up to 2 of WL gamma K is equal to what? Well, it's the variance of these things, which was 2 over n L minus 1, times the delta function that you had the same weight. Otherwise, you got 0. Right? But to have the same weight, it means they had to pass through the same neuron on layer L minus 1. And they had to pass through the same neuron in layer L. Okay, and as was correctly pointed out by several people, this just means that in this whole sum, I only get a single path that contributes. So it looked like I had two, but they have to be the same path. Okay, so what do I get? So and this is really kind of like the third step. Because this mean 0 thing, anything over 2k paths collapses to just k paths. Okay, so I get that this expectation dz L plus 1 q alpha by dx p alpha squared, okay, very exciting, right, is just equal to, so let me write this very carefully. So I get the sum over just a single path, gamma from P to Q, right? When the paths are the same, these indicator functions are the same. So each one of these expectations just gives me a factor of 1/2. It's on with probability 1/2. And what do I get? So I get 2 over n capital L. That's from my weights in the last layer. And then I get this product. Okay, I get the product, and little l goes from 1 up to capital L of 2 over n L minus 1 times 1/2. And that 1/2 came from the size. Okay, this is looking eminently calculable at this point, right? Everything magically collapsed and disappeared and all that. But let me belabor this for just one moment and factor out all these constants and write this in a funny way. Okay, so you see that the 2's cancel. That's why for ReLU networks you need variance 2 over n minus 1, because each neuron is on and off with probability 1/2 and it kills half your variance. Okay, this 2 you don't care about, it just appears once, and it's because I was lazy and didn't rescale the output weights. So I get, okay, 2 over n0, okay, I'm re-indexing this product. You see I have an nl minus 1 here, so I shift everything to the right by 1, and I pick up an n0. Okay, I get a product on L goes from 1 up to L of 1 over NL now. And then, okay, allow me for one moment to write this in a funny way. It's just the sum of 1 over these paths. It's going to count the number of paths. Okay, so of course you can easily count the number of paths. We're about to do it. But let me point out that this has a very nice interpretation, right? So note that. It's not just a sum over paths. Actually, this prefactor here turns this sum into an average over a random path. Okay, that's the key point of the yoga in some sense, right? So the number of paths, gamma from P to Q, is what? Right, well, I tell you which neuron to start at. I tell you which neuron to end at, and then I have n1 choices for neuron in the first layer, n2 choices in the second layer, and so on, right? So it's just this product on L goes from 1 up to capital L of NL. And so you see that I just divided by the number of terms in this sum. Okay, so thus, what do I find altogether? I find that the expectation of this squared derivative, ZL plus 1 Q alpha, X P alpha squared, okay, is equal to this prefactor, 2 over N0, okay, times what I'll write is script E sub gamma of 1. Okay, where what is this script E? Okay, I'm keeping you in suspense. That's how I do it.
Is N0 there too, right? In the expectation?
Sorry, say it one more time, please.
In the expectation on the third board, it's 2 over N0.
No, because you choose a path, I think you start from the point B and then you first have N1 choices, then N2 choices, then N3 choices.
Yeah, exactly. Because I told you the starting point, you don't have freedom about that, right? Yeah. So these are all kind of the right questions to ask, and you have to sweat the details when you write the paper. But for now, you can basically just chill out, and it's true, but you're right, it's a good question. So what is this E sub gamma? Okay, the point is that this E sub gamma is equal to the average over a random gamma, a random path gamma, which is chosen in the simplest possible way. Okay, so it starts at P, it ends at Q, and all the other ones are just chosen uniformly between 1 and NL, independently of one another. Okay, it's the stupidest way of choosing a random path. So in this mean calculation, it's particularly simple. It's just the average of 1. But this happens when you do all these calculations. In the end, you do some combinatorics on the paths, and you get some nice prefactor, and then you get an expectation over some number of paths of something that just depends on the combinatorics of the paths. Here it was trivial, it was just 1. The only combinatorics was that they had to collide and be the same everywhere. But if you do more than 2 paths, you get a more interesting expression here, which is something about like a penalty for colliding. Okay, good. But of course, this is just 1. This is 2 over N0. You didn't really need that interpretation for the mean. Okay, very good. So let me just pause for a second and ask about this. I tried to do it very slowly because that's the yoga of the paths. You put in the paths, you use the independence, you go from 2k paths to k paths, then you turn it into a mean, and then you hope you can compute. Okay, which you always can because somehow the gods love random ReLU networks, seemingly. Okay, so questions or comments about this?
So in when you do like fourth moment, you can have like say together cover each edge twice, but they are not identical.
Precisely, that's exactly what's going to happen. If you had 4, then you reduce from 4 paths to 2 because every edge has to be covered an even number of times. But then there's a combinatorics about how to go from those 4 paths that cover an even number of edges to just 2 paths. There's many ways of going from 4 to 2, and you have to take that into account. But okay, it's not that bad. Okay. So yes, that's exactly the difficulty, but it's not too bad. Yeah.
What is the relevance of setting the biases to 0 for these calculations?
For this calculation, absolutely nothing. So I want to do the mean of the, so I wanted to do the 4th moment, which actually would not change anything. Let's see. So the short answer is nothing. I just didn't want to write them. I remember what happened. I was going to present a slightly different calculation, but I decided not to. Okay. So you don't need the biases to be 0, but all right. Very good. Thank you. Sorry about that. Other questions?
How did we get
Yeah.
the mean 1?
So, well, we just had 1, and then the number of terms in this sum was exactly this product. So it's an average over a randomly chosen path. So somehow observing that is key. You can't do the calculations, or I don't know how to do them without this observation. It turns everything basically into a Markov chain on paths. You go from layer to layer, you pick up some. Okay. So, okay. Let me do this. Let me just take yep.
Sorry, just quick. How did you get that note again?
This one?
Yeah.
So you see, okay, I erased my weights, but this is going to be 0 unless the 2 weights are exactly the same. But in order to be the same, they have to come from the same neuron, and they have to end in the same neuron. And so you get the delta function on both sides. Yeah. Yep.
I think that with a convolutional network, the dependence of these average would still be over 1 over M0.
Yeah. So good question. So it turns out for this mean, you can do it for convnet just fine. And instead of 1 over n0, you'll get like 1 over your kernel size times number of channels in the input. This is just like the variance of the weights in the first layer. Okay, you'll get an extra 2 in there too. If you want to do the higher moments, it's more complicated. In fact, I had a student write a senior thesis about that last year. Okay, it's not too bad, but there's more stuff because of weight sharing, as you can imagine. Okay, so question, do people want to see the 4th moment, or do you want to see the mean of the NTK? 4th moment. Mean of the NTK? Oh God, the mean of the NTK wins, I'm sorry. I'll show you after if you want. Okay, so let me just put a box at the end of this proof. The 4th moment's also in the notes, but I'm happy to tell people if they want. So let me also now state a result about the NTK, and you'll see how you can use these calculations to figure out how to set learning rates and everything, at least in the NTK regime. Okay, man, I'm going really slowly. Okay, that's good. It's good. Slow means potentially comprehensible. Okay, so here's my theorem. Okay, so consider the NTK, and okay, I'll write it as capital theta as per convention. So I'm going to actually define it like this. So it's going to be a sum over mu. So mu are weights in the network. And I'll actually put in the learning rate of each weight, eta mu. That's actually the thing that comes up when you write down the NTK update equation. So I prefer to put in the etas directly into my definition of the NTK. And then I'm going to take the derivative of the output neuron in my network. Here I just assume I have a single output, or I'm studying the NTK of a single output squared. Right? This is precisely the NTK on diagonal. It's just the sum of squares of the derivatives of your model output with respect to the parameters. Okay, I weight it by the learning rate of each parameter. All right, so then, this is what I'm going to show you. I think we have just enough time for this, hopefully. Okay, you can calculate the expectation of the NTK. So let me call this NTK after L plus 1 layers. It looks like this. So I get 1/2, and I get the sum on L goes from 1 up to capital L. And then I get the learning rate in layer L of the biases, plus the norm of the input squared over the input dimension, times the learning rate of the weights in layer L, times NL minus 1. Okay, it's an exact formula. Just like the mean, there's an exact formula mean of the derivatives, there's an exact formula for the NTK that looks like this. So I'll show you how to derive it. It's really not very hard, I promise. But I just want to point out, you already learned something which you already knew from other kind of points of view. You see, if you're not careful to take a small learning rate, at least in the NTK parameterization, for your weights, nothing's going to work out. So this tells you that the learning rate for the weights needs to scale like 1 over n. Okay, and that's indeed what people need to do in practice to get the NTK regime to work. However, interestingly, the learning rate from the biases definitely does not need that. It can be order 1. Okay, so from my point of view, this is one of the things I was trying to allude to last time. One of the utilities of doing these calculations at init, if you can do them at finite width, is it can tell you how to scale learning rates, how to scale initialization schemes, and so on. So the mu-p calculations that I think a lot of you are familiar with do exactly this kind of thing. It's a slightly different scaling, but all the same techniques work just fine. And you can really get the effect of depth and of width and everything if you want. Okay, so that's what I want to check. I'll erase, and then I'll take questions, and then I'll calculate. It's basically the same calculation that we already had, but I will answer a question that I think Yasman was asking me before, but why derivatives with respect to parameters are the same as derivatives with respect to inputs. It doesn't feel that way, but it's true. Well, sort of true, you'll see. Okay, is this okay? Is it clear what I'm trying to do? Okay, I just want to calculate how big the NTK is. And from this, you see how the coupling constants should scale with the width. Okay, or sorry, the learning rates should, right. Okay, very good. So let's do it. Okay, I have plenty of time. I can do this. So, okay, so let me compute the following. So let me write NTK alpha alpha looks like this, right? It's a sum over all the parameters. I have parameters in every layer, right? And then I have the following. So I have biases. So maybe I'll call this J, goes from 1 up to, maybe I should call this I, up to NL. Right? And this is the learning rate in layer L of the biases times the derivative with respect to my bias of the output, ZL plus 1 alpha squared. Right? That's all the biases in layer L. And then plus, I need to sum up over all the weights. So I have an extra sum. I goes from 1 up to NL minus 1. Sorry, this should be a J, in fact. Since this was an I confused myself. Right? This is eta LW, derivative with respect to the weights in layer L, IJ, ZL plus 1 alpha squared. Oops, what did I use? Like that. Okay, very good. Okay, so I'm just writing it out in some horribly explicit way. And when I compute the mean, I can just compute the mean of the weights and the mean of the biases separately and then add them up. And that's what I'm going to do. It's not too bad. Right, so let's compute this. So what's the expectation if I take the derivative with respect to a particular bias somewhere in my network of the output? Okay, well, what does backprop tell us about how to compute this? Right, and this will be this point about derivatives with respect to parameters being like derivatives with respect to inputs. So I'm just supposed to use the chain rule. Right, this is the expectation derivative with respect to the bias of the post-activation of this neuron, ZLI, times the derivative with respect to this post-activation sigma of ZLI of the output, ZL plus 1 alpha. I guess there should be alphas everywhere. Okay, and this is all squared. Right? The bias at layer L in neuron I affects the output only through this post-activation. But you see, this is nothing more than a sigma prime. It's one of my psi indicator variables, whether or not the neuron's on or off. So this is just the expectation of what before I called psi L. Sorry, let me just write it this way. This is the expectation of sigma prime. That's probably the best way to write it. I alpha squared. Right? Just 1 if it's on, 0 if it's off. Times this derivative. Right? And this is just the derivative of the network output. Okay, with respect to the post-activation in some layer, which I just think of as a network input. I just forget about everything else in the network, and I think of this as the derivative of the output with respect to this particular input. I can do that. No one can stop me. D sigma of ZL I alpha, okay, also squared. Right, and so what do we know? We know that these two things are independent, and we know the size of both of them. So we get that the mean of the first one is a half, and the mean of the second one we just calculated, it was 2 over the input dimension, but now the input dimension is my hidden layer width, NL. Okay, so I just get that this is 1 over NL. Okay, very good. Now I'm worried about this 1/2. Pretend you didn't see it. I think this is going to be fine. Okay, so my point is the derivative with respect to biases are easy. We have already had the formula for them. But the derivative with respect to the weights are going to be very similar. It's just we have to use a slightly different formula, right? So finally, what do we get? So remember that the derivative of the output with respect to a weight was a sum over all the paths that go through this weight. That's the kind of formula I'm going to have to use. So I get the expectation. Okay, I can do it. DZL plus 1 Q alpha with respect to this weight, Lij squared. Okay. So see if I can remember the formula. Hopefully I can. So I think it was the sum on P goes from 1 to N0, the pth component of X, times the sum over all the paths that go from P to Q and that go through this weight. So gamma of L is equal to I, gamma of L minus 1 equals J. And then I had this product of weights out here, right? Gamma L plus 1, sorry, WL plus 1 gamma, product on L goes from 1 up to L, WL gamma, CL gamma, oh my God, so many gammas, okay. WL IJ, I should probably call this L prime. I apologize. Okay, it's all of this squared. Okay, so I'm just saying, like, you might not enjoy it a lot, but it's pretty short. You just have to write this out. And now we're going to play the same game. We're going to square this thing. We're going to get a sum over 2 paths, okay, just like we had for the mean of the input-output Jacobian. It's just one of the weights will be missing from this product. That's all we're going to have. Okay, very nice. So let me write this here. Okay. So what do I get? I get P1, P2 equals 1 up to N0, X P1 alpha, X P2 alpha, right? The sum over gamma 1 goes from P1 to Q. Gamma 2 goes from P2 to Q. Okay, allow me to drop the condition that both of them have to contain the W's. So let's just remember that. And we get this expectation. Expectation, I get the product on K goes from 1 up to 2. K of these output layer weights, gamma K, times everything else. So I keep writing the same thing. Let me write it this way, L prime, okay, gamma K, C L prime gamma K. Okay, and here let me just take the product L is not equal to L prime because I have to divide by that particular weight. Right, so all I'm missing is the weight in layer L prime. Okay, so you get this kind of formula. And again, what do we see? Right, so let me try to draw the picture with my favorite network architecture, which is apparently a Christmas tree looking thing. Right, so I had some particular weight that I wanted to differentiate with respect to. This was my WLIJ. Right, and I had to take paths that can do whatever they want. They start here, but they have to go through this particular weight. So W1 can do this, and then it can go through here, and it's got to go to the output. And my path W2 has to also go through this weight, and then it has to go to the output. So that's the kind of thing I get. So here's gamma 1, here's gamma 2. They have to stay together here. And okay, in my small picture, they have to stay together here as well. Okay, so what do you notice about this expectation? Well, just like before, there's only 2 weights in each layer. Right? And so therefore, again, this sum over 2 paths collapses to a sum just over 1 path because they have to be equal. Okay, so what do you get? You just get that the p's have to be the same. So you get x p alpha squared. That's where we're going to get the squared norm of the input. And then you get the sum over paths from P to Q. Okay, and you get almost the exact same answer we had before, except that notice you're missing one of the weights. So you're off by a factor of 2 over NL. You don't have that particular term. Okay, so you have 2 NL minus 1. That's the factor you're missing from missing that particular weight. Okay, times this product. So you get 2 over NL like before, and you get this product on L goes from 1 up to L of 1 over NL minus 1. It's the same exact calculation we had. Okay, and what you see is that other than this factor of 2 NL minus 1, it's all the same. So, okay, I seem to be getting a slightly different constant than what I had in my notes. We'll chalk that up to some kind of numerical error, right? This thing gave me an extra 1 over N0. So, in fact, it gave me a 2 over N0, as I recall. Okay, and that's it. That's the answer that I get. Okay, so I had a 4 instead of a 1/2. Not sure what happened. But when you sum all this up, you get exactly what I was saying. Okay, you get that each of these eta LWs has an extra NL minus 1 in front of it. So that's kind of sad, and you have to deal with that fact. But otherwise, the eta B's just nicely cancel. Right? The 1 over NL from this thing exactly cancels the sum on I goes from 1 up to NL. Okay, so that's how you do these calculations. These are the two simplest ones I know, just the mean of the input-output Jacobian and mean of the output parameter Jacobian, basically. Okay, so let me put a box here. Maybe I won't finish this. Let me just ask for some questions or comments, and then I want to tell you a bit more, in a sense, about what you can do with these things. Okay, so other questions or comments about this? I know I sort of went through the end fast, but I promise it's exactly like the first calculation that we did. I know there's a question or comment somewhere out there, so I'm going to wait for a second. I feel it. I feel it in my bones. Lincoln knows what I mean. Okay, so let me do this. Rather than trying to rush through the fourth moment calculation, which is fun, but takes more than 15 minutes, let me zoom out a little bit and try to, well, for everyone, but mainly in a sense for the PhD students, to try to formulate some questions that I think are open and interesting about random networks and things like that, rather than trying to state more results. I think I gave you the flavor of what you can do. Yeah.
Is there some intuition just with the form-one calculation why the kind of L over N term would come out? Would be that, suppose all widths are N, then the probability that two paths do not collide is, so a pair of random paths does not collide is like 1 minus 1 over N to the power L.
Yeah, so
and if they collide, they kind of contribute more to the fourth moment than they would otherwise.
Yeah, so fine. So since you're asking, let me write one formula about that, because that's exactly the right intuition. Okay, so what happens, for instance, for 4 paths, let me just skip all the calculations and tell you what the answer is. So if you took this derivative and you tried to compute the fourth moment. So what do you get? Okay, you get a constant, it turns out it's 6 over N0 squared, times you get the expectation over 2 uniformly random chosen paths that go from P to Q. And the kind of thing you get is you get a product on L goes from 1 up to capital L of 1 plus 5 times the indicator function that gamma 1 of L is equal to gamma 2 of L. That's the leading order contribution. Somehow when they come together, you pick up some extra combinatorial factor. And that's exactly what it is. So the probability that they come together in layer L, because they're independent and everything is uniform, is 1 over n. And so this thing exactly scales like exp of 5 times the probability of these events occurring. And that's this sum of probabilities. Okay, plus some lower order terms that I was. So that really is how it comes out. And if you have k paths, then you pick up a bigger factor here, and it's more likely that some pair of them collide, so you get some k choose 2 thing. It's basically like, because L is large, you get a Poisson number of collisions that occur. And that's the kind of expectations you get for this, yeah. Exactly. Okay, other questions or comments about this before I try to give some open problems? Okay, very good. So let me connect very briefly first to what Julia was telling us. So there's a beautiful series of papers by people like Sebastian Bubeck and Peter Bartlett and some other people as well. So one thing I think is kind of cool is the idea is to look for adversarial examples. Serial examples in random ReLU networks. Okay, so they have some results, but the results are very incomplete, and the idea goes like this. It says, well, maybe the presence of adversarial examples is not really about how much training you do and exactly what happens. It's just that you're in high dimensions, and if you give me an input, there exists some direction to go so that I don't move too much, but I flip the label of the prediction that I get from my network. And you know, I would say that like really getting tight bounds on how this works is not fully understood, and it would at least give a very simple baseline for whether or not you have more or fewer adversarial examples after training, for example.
You are completely isotropic. You are suddenly becoming invariant, right?
Yeah.
Because you're fully symmetric. Doesn't that mean that one adversary becomes fully symmetric? I mean, doesn't an adversary translate to random noise then?
Yeah, the question is like this. You take a realization of a random ReLU network and you give yourself an input. You know, like, it gives you some prediction, and now the question is, what's the nearest point to your input that flips the prediction? Now, surely the only thing that's interesting, as you say in this example, is the distance between your input and the adversarial example. The direction will have no meaning, essentially. But still, just to get a baseline for how far you are. That's like a reasonable question. And it's kind of about the geometry of the function computed by a random ReLU network. So I think that's a nice thing.
So it's basically the Lipschitz constant of a random value.
Yeah, so exactly, okay, you took the words right out of my mouth. So an interesting open problem, which kind of is actually harder in a sense than this adversarial problem, but certainly would imply it. And this is still genuinely open to compute good bounds on the Lipschitz constant of a random ReLU network. Okay, so let me just contrast that with what I did in this lecture. You see, the Lipschitz constant is the biggest that your Jacobian can possibly be over all the inputs. That's one way to say it. What I did is I fixed an input, and I told you how big the Jacobian is typically at one input. And so the difference between what I did and this is you need to compute a soup. Okay, well, the soup of a process is harder to compute than its like mean at a point. And it's like somehow hard, and you see that these methods are not obviously good for it because this involves many inputs, not just one. But I think this is a very nice problem because, you know, you can bound generalization error based on Lipschitz constants, for example. So you might hope to know how big is the Lipschitz constant at the start of training. You know, I think that's a sensible question.
But
Yeah.
I mean, what you can do with this framework is to compute correction to the Lipschitz constant that comes from finite width, because I guess you can do that analysis by just using the GP limits that Jasmine told us about, right? I mean, you know you're not with the GP, so you know.
So
Maybe it's going to be all the continuous with more than 1 and 1.
So correct. In the infinite width limit, this reduces to like a really famous, like classical kind of question. Compute the distribution of the maximum of a Gaussian process, where your Gaussian process is like the gradient of the GP you get at infinite width. So you can certainly do that. That's already not such an easy calculation, but we know a lot about that kind of thing in terms of the regularity of the covariance function. But here the question would be, how does it scale with depth and width and all of that in a practical network? Okay, fine. So that's one set, I think, of interesting open directions. Okay, so the second set of directions is something we touched on very briefly before, but I just want to emphasize. You know, I am really interested in connecting all the ways you can actually get feature learning that we seem to know. Okay, so I want to connect taking large learning rate with mean field and large depth for feature learning. Right, so Yaseman was telling us, for example, that you have this interesting catapult phase. If your learning rate is large enough, you really quickly leave the NTK regime right at the start of training, and you actually go and learn some interesting features. Maybe we don't know 100% what those features are. That's one way we can get feature learning. right? And then lots of people, in particular Andrea and Eric, were telling us about mean field scaling. If you scale the outputs of the network in a non-NTK way, then actually you can learn features even at infinite width, so that's a beautiful thing. And so like, to what extent are these really the same thing? Okay, there's some results about that, but I don't think it's fully understood. And the point of the lectures I was giving is that there's yet another way to learn features, which is just take NTK everything, but take large depth. And are they related? Are they orthogonal? Are they just like some kind of rescalings of one another? I don't know. Okay, and I don't think anybody really knows, but I think it'd be really nice to understand the different ways that feature learning occurs and in what senses they're related. Okay, yeah.
Generalization bounds aren't they related to Lipschitz constants for a train network, not
Oh yeah, sure. But so this would give you like a baseline, first of all. Second of all, you could imagine saying, if I knew the Lipschitz constant at initialization, I could imagine tracking the change in the Lipschitz constant through training. And then you would get a bound on the Lipschitz constant for your train network as well. So that step is non-trivial for sure. But like, if you can't answer this question, there's sort of no hope, to answer the question of the Lipschitz constant after training. At least I think. So like, I view it as a kind of interesting question for a variety of reasons. People also use random ReLU networks, if you know what like the deep image prior is or other things, as like ways of either compressing or like interestingly generating like actual realistic looking images. And so there, when you're talking about those kind of GANs or that kind of thing that people use for compressed sensing, the Lipschitz constant is important. You don't want things to fluctuate too much. Okay, fine, very good. So let me try to state at least one more open problem, which I think is kind of nice. And I will stop. Okay. Good. So we've been talking a lot about trying to calculate things at finite width here, and one of the main reasons was, although I didn't do these calculations, you can try to track through training, at least at small learning rates, what happens and how much you deviate from the NTK regime. So this is hard but doable, and what I'd like to do is I'd like to propose, okay, if you like the two lectures that I gave, to do path counting or something analogous to it for general sigma. So I did it here just for ReLU. So things for general sigma will be slightly more complicated. But the reason I care about this is, you see, for ReLU, I can really tell you that things depend on L over N. I don't have to cheat. I don't say that things, right? So in the previous lecture, I said something like I had this fourth cumulant. And I told you it looks like a constant times L over N plus O of N inverse. And then I threw my hands up and I told you that I'm actually a lying cheater, right? This thing here is really, honestly, O of L over N squared. That's the dependence on L. And so really, I can only, using the techniques in the previous lecture, access the regime where L over N is small. And the point of the path counting, for me, one of the things I like about it is I can tell you what happens when L over N is order 1, anything you want. And so understanding that regime for general sigma, I really don't know how to do. And I'm not sure if it's the path counting that should be extended, or you take this previous method and you try to do a resummation of your errors. I've tried a bunch of things and I've been unsuccessful, but maybe you will have better luck. Okay, so I think it's nice, at least from the point of view of these NTK type networks. If you're going to be close to the NTK regime, you better take your depth to be large so you can learn some features, but then you need to know the effect of L over N instead of just kind of the leading order contribution, ideally. Okay, so I have a couple minutes left, but let me just not try to run over time. Let me instead ask for questions or comments about anything that I've said. Yeah.
I have a question. It's really also to the crowd about kind of empirical results that we have about the scaling with the depth. Like some of the scaling laws, they grow number of parameters because they grow the width. Are some of those results also actually growing the depth and looking at the scaling?
Yeah, so I think that's a great question, first of all. But let me answer it in the context of one very specific thing. So you probably know about this mu-p story. If instead of initializing quite like NTK, you initialize the last layer weights to be small, so you're more mean field, there's some really seemingly stable prediction for how to scale the learning rate as a function of width. If you know what it is for small width, you can set it for larger width as well. So those results don't work when you scale the depth. the optimal learning rate changes. But okay, using this technology, I'm almost done writing a paper with my student who's at Google right now. We get the depth dependence as well, and you can see it come out. So you can actually do that analytically as well. And so like, I think that's like a very small example of the kind of question you're asking about. You know, when we like draw the x-axis in double descent, for example, we just say something like number of parameters, but that's sort of a horribly underspecified thing, even if you mean fully connected network or something in the background. And what I'm saying is things really will change as L over N differs. You know, maybe the shape will be the same, but like the exponents could be different, or, you know, all kinds of things could be different. And yeah.
What I gathered from your lecture, I was just wondering, you know, I don't have in mind like maybe people did some more of that.
Yeah, so I personally don't know. Maybe someone in the crowd knows. Do people know the depth scaling of the double descent curve? If you compare similar models at different depths, what happens?
I mean, the thing is that if you change the depth, as far as I understand, it's empirically sort of, the empirical idea is that the depth doesn't affect so much results for fully connected network. Whereas if you have a complex architecture, you do have dramatic changes, but also the kind of function you represent change. So how can you put everything?
So
You have a fundamentally different model.
yeah, I don't think that can be quite right. Like, I'm going to channel my inner naughty.
Disagrees with what Boris is telling us.
Yeah, I channel my inner naughty and I say all these networks optimize over all possible functions. With depth 1, depth 100, you're always in principle going to represent. It's just a question of the bias that your architecture gives you for what you learn, and that changes dramatically. And I'm saying I do think that that's going to change a lot with depth, and it might be more dramatic for a transformer, for example. Like I don't know, but like that's something maybe you could see analytically or maybe not. I'm not certain, but like. I still think you're going, like, I think even for fully connected, you'll get an effect like this. That's what I'm saying. And I think you might be right that it might be more dramatic for other architectures. And I'm not sure. Maybe Yaseman knows. I know you guys have done a lot of empirics. But I don't know if you track the dependence on depth of like double descent curves or anything like that. No. So.
Is the question about any metric, like double descent or sampling complexity?
Not so much double descent.
Oh, okay.
Yeah, more like the test error, how does it go to zero with depth, right? More about kind of the scaling. I mean, in essence, this kind of theory, right? It gives us the scalings, like L over N.
Right.
And so, are there actually, maybe that would be just interesting to do some set of experiments that would actually look at something like that.
So I think it would be interesting. I don't know of experiments like that. It can be a little painful because if you imagine that L and N both have to be big, and then you have to vary them. But I mean, if you just have a lot of compute, you just,
Yeah, but
you know.
people look at number of samples, people look at width, people look at all several kinds of things for these scales also.
Right. No, I agree that it would be interesting to know, and I don't know. I suspect the answer is yes, but I don't have an experiment to back it up. You know, I don't have a theorem to prove it either, so, you know. Okay, so maybe let me stop there, and I thank you for your questions and attention and all that.